Rosenblatt, the guy who actually started with the whole of machine learning and artificial intelligence, he started with an IBM digital computer, but then because it was too slow for him, he moved on to an analog computer. Should we do the same? So here's the deal. Digital computers are very accurate because you're talking in specific numbers, ones and zero. Analog computers are not accurate because you have a whole range. You can produce a sine wave with an analog computer. To produce a sine wave with a digital computer, we need many ones and zeros. Also, in order to answer differential equations, which are analog on their nature, we need lots of operations on digital computers, while on analog computers, this can be solved easily. In addition, analog computers can be very specific to a specific problem, and we have already seen this in machine learning and in AI, where we utilized in the ImageNet, in one of the early years of ImageNet, which is the thing that has started the resumption of the AI, and then someone started using GPUs, because we need matrix multiplication, dot multiplication of matrices, of vectors. And GPUs can do very specific operations in parallel. As long as they do the same operation, they can do it in parallel. So GPUs were very beneficial. So maybe analog computers as another specific computing platform, just as GPU is very specific computing platform, can serve us very well. And yes, there is a startup in the United States which deals with it. It has a very small chip in a few centimeters that consumes only 5 watts, that can do what a big GPU can do. But of course, there are also limitations. First, this technology is relatively new. Who knows, in 50 years, we might look backward and say, oh, those digital computers, what an old technology for machine learning and AI. We all needed analog computers. So how do we do multiplications in analog computers? So the current in a wire is equal to the volts times 1 dividing 1 by the resistance, by the inverse of the resistance. So we have a multiplication equation. So if we plug the right resistance and the right volts, we get a specific current, which is a multiplication of V times the inverse of resistance. Very simple. So all we need to do is to play with the resistance, play with the volts, and we can do multiplication for addition. We can also add multiple currents on parallel, and we get an addition of currents. And of course, especially these days, that we are reaching the time when the smallest unit of digital computers approaches the scale of atoms. So we have reached the Moore's law, the end of Moore's law, maybe, but maybe we'll begin a new area of incrementing the power of digital computers by moving them into being analog computers, and with this we'll continue breaking the Moore's law. Also, our brains are partially digital and partially analog, because we need a specific set of currents in order to pass the threshold. This is the perceptron. And only if we pass it, then we spike from 0 to 1. Okay, we ignite the next neuron. So this is a combination of analog and digital. So maybe we need the same thing in computers. We already have actually the current in the wires on the computer is analog. He's not aware of zeros and ones, right? The atoms are not aware of zeros and ones. We already use a combination, but maybe we need a larger combination of analog computers taking a bigger role in the AI, just as Rosenblatt has discovered about 50 years ago when he solved his AI problems with an analog computer.